All right, welcome back, everyone. So before we get started on our new material today, I want to talk about the exam that happened on Monday because there were definitely some issues with that. So I think I already sent an announcement about this, but I'll just write it again just in case you didn't see it. So on exam 3, question 3 didn't show up. Actually, I'm curious, did it show up for anyone? Was anyone actually able to see the graphs? Was anyone actually able to see it? Oh, someone said they saw it. Huh, that's so bizarre. Yeah, I still have no idea why that didn't show up. But anyways, because it didn't show up, we just threw the question out. So unfortunately, that means if you happen to guess it correctly, and actually literally almost everyone guessed on it, very few people left it blank. Everyone was trying to get the points there. But unfortunately, I can't give points for just being lucky and guessing that. So even if you got points for that, you don't actually get to keep them. So the maximum grade is now going to be out of 93 rather than 100, because that question was worth 7 points. All right, and then another issue that was brought to my attention here is question 11, and I think it was part B, the error for that calculation, which I think was approximating natural log of 5/4, if I'm not mistaken. So the error that you get from that, the upright bound for the error would be 1/192. But this was not an answer choice. Okay, so since it wasn't an answer choice, but you could actually have attempted that problem, so that problem was visible and you could do it, I decided to just give everyone 2 points for this problem. So if you did not get it right, then you got 2 points. If you got it correctly, then you got to keep those points. So that's how it ended up going. So the grades ended up being out of 93 right here. And the average was about 70%, which is actually, it might sound kind of bad, but it's actually a little bit higher than average for exam 3. So overall, you guys did pretty well, despite it being a flawed exam right here. All right, even if it didn't go so well, don't worry. We still have the final coming up. So you have one more chance to redeem yourselves before the end of the semester here. All right, well, enough about that. Let's go ahead and get to our lesson for today. So we have 2 more lessons. So we are going to talk about polar coordinates, and then we're going to talk about calculus of polar coordinates on Friday. And then next Monday and Wednesday will be review for the final exam here. And yes, it is going to be a cumulative exam. Does it focus on the new material mostly? No, it's going to be kind of an even distribution of all of the material throughout the semester. So integrals, series, power series, parametric equations, and polar. All right, so let's go ahead and get started here. Make sure we have enough time to talk about polar coordinates. So today's lesson 32. As I said, it's about polar coordinates. All right, so as I said in the beginning of the semester, essentially the last part of Calc 2 exists because there's not quite enough room in Calc 3 for everything that we need to discuss. And one of the things we're going to be using a lot in Calculus 3, if you choose to join us for that class, is we're going to be using polar coordinates quite a bit. Okay, well, what are polar coordinates? Well, before I introduce those, I want to remind ourselves about the coordinate system that we're most familiar with. There's the Cartesian coordinate system. And the way the Cartesian coordinate system works, as I'm sure you're all familiar, is if you have a point, it has an x coordinate and a y coordinate. And the x coordinate tells you how far to move to the right if it's positive or to the left if it's negative. So this distance here would be our x. And then the y tells us how far up to move or down to move if it's negative. So by specifying these 2 directions right here, we can uniquely identify points on the plane right here. All right, now it turns out that there are other ways of uniquely specifying points on the plane. So rather than telling you how far to move horizontally, how far to move vertically, we're going to explore another way of identifying points. The other way, polar coordinates, what we're going to do is we're going to imagine that we start at the origin, right? And let's imagine that we're looking in the direction of the positive x-axis. So theta equals 0. So let's imagine we're looking this way, theta equals 0. And what we're going to do is we're going to begin rotating counterclockwise until we're looking at the point that we want to go to. So I guess I need to rotate around this much, and then I'm looking from the origin to my point xy right here. So this is going to be our angle theta. We rotated through an angle theta. And then what we do, once we're looking at our point, we walk out to our point, and the distance that we go out is going to be called r right here. So in addition to specifying a point as x and y, you can also specify the points r and theta values. So how much you need to rotate to be looking at the point, and then how far away from the origin your point is going to be. And these are called polar coordinates. Okay, now one question that may be on your mind is, well, we have a perfectly good system already. I'm already comfortable with doing the horizontal and vertical distances for x and y. Why do we need to bother with a new system? Why do I have to learn these new things? It turns out that polar coordinates are good at representing things with radial or circular symmetry. So Cartesian coordinates, which are also called rectangular coordinates, are good at specifying things like lines or planes or things like that. But polar coordinates are a bit better at expressing things like circles or cylinders. And when we get to calculus 3, we're going to need to express a lot of different shapes or express equations for these different shapes. And many of these surfaces or curves that we're going to look at will be much more easily expressed in polar coordinates as opposed to x and y here. This is kind of similar to parametric equations where there are some curves that just we can't easily express in terms of x and y, so we use parametric equations. It's kind of the same thing here with polar coordinates. All right, now let's take a look at this picture here. Now, one thing we're going to need to do in the future is we're going to need to convert between Cartesian coordinates and polar coordinates. So we may be given a problem, for example, in Cartesian coordinates, but it may be more natural to complete that problem in polar coordinates. So how do we get from one coordinate system to the other? Well, it turns out that we can use trigonometry, in fact, it's about the unit circle, to give us our conversion equations. So for example, this kind of picture here formed a right triangle, right? So what's a relationship between x, y, and r? What's something that I could write down with those variables? Yeah, that's right. We could write the Pythagorean theorem, or x squared plus y squared equals r squared. So there's one of our conversion equations right here. Another thing we can do is we can express a relationship between theta, y, and x. Yeah, so Noah has the right idea here. What we're going to do is, since y is the opposite side of this triangle, and x is the adjacent side of this triangle, we then know that tangent of theta is going to be y over x. Now, another way you may see this written is that theta is arctangent of y over x. But be a little bit careful with this, because remember, arctangent only goes between negative pi over 2 and pi over 2. But sometimes we might be, say, in the second or third quadrants here. So I personally like this equation better, but you also will probably see this one too. All right, if we want to have a relationship between Rx and theta, that's going to be x is r times cosine of theta. And we can see where this comes from if we divide both sides by r here. This is going to be adjacent over hypotenuse. And then can you guys guess, if I have y equals something with r and theta right here, what do you think I'm going to write for that? That's right. It's going to be r sine of theta. Oh, did someone just guess that I was going to write x as r cosine theta? Yeah, kudos to you. That's pretty perceptive. But yeah, that's right. So we're going to have y is r sine of theta right here. So these four equations right here, and possibly this one if you like, these are going to be our means of switching between polar and Cartesian coordinates here. All right, but before we even start switching back and forth, we want to get used to just using polar coordinates on their own. So this is going to bring me to my first example here, example 1. So let's plot the following points given in polar coordinates. Now, traditionally in polar coordinates, we specify the r before the theta, just like we always seem to express x before y right here. So here are these polar coordinates. We have 3 pi over 3. We have 5 pi over 2. We have negative 2 pi over 4. And then we have 0 pi. All right, so let's see if we can plot these. All right, so I'm going to draw my axes here. All right, let's take a look at our first point here. So this has r equals 3, and theta will be pi over 3. So kind of in the way that I described that we created polar coordinates up here, I'm going to use that same reasoning to figure out where this polar coordinate leads us to. So I'm first going to do theta. I'm going to rotate pi over 3, so maybe about that much. And then I'm going to go out 3 units. So 1, 2, 3. So maybe we could say it's like this. And then we arrive at this point right here. So we could label this point as 3 pi over 3 in polar coordinates here. Okay, let's take a look at the next one here. So this is my r, this is theta. And this is going to be one of our first kind of idiosyncrasies of polar coordinates here. There's some weird properties of polar coordinates that didn't really exist in Cartesian coordinates. So we're going to rotate through theta, right? So 5 pi over 2. So this is pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, or 2 pi. So we've actually come full circle. And then we go an additional pi over 2. So it seems like we're looking this way. So we spun all the way around the circle, and then we spun an additional pi over 2. And so we're looking in this direction, and then we go out 1 unit. So maybe that's like right here. So we're at this point. Now, let me ask you guys this. Is there another way that I could have expressed this point in polar coordinates? Maybe a little bit of a simpler way? Yeah, 1 pi over 2, that's right. So this is kind of our first interesting fact about polar coordinates. So with Cartesian coordinates, if the numbers I put here are different between 2 different points, they will correspond to 2 different locations of the plane. But with polar coordinates, I can have different numbers, say in the theta slot right here, and it points or it leads to the same coordinate right here. So it shows that there's actually more than one coordinate representative for each point that we have. So 5 pi over 2 leads to the same place that 1 pi over 2 leads. Now, in some contexts, what we do to remedy this situation, if we only want one representation for each point, is we might limit theta to be between, say, 0 to 2 pi or negative pi to pi, like that. But on the surface, there's no reason to do that. It's contextual based on what we're doing. All right, let's move on to our next point here. So this one's not too bad. We just rotate to pi over 4, which maybe is like a little bit shorter than pi over 3 here. And then this one says negative 2. So if this said positive 2, what I would do is I would go 2 units in this direction, and I would be somewhere here, right? But if we ever get a negative value for r, what we do is we instead go in the opposite direction. So normally I would go this way, right? But instead I'm going to go 2 units in this direction. So I'm actually going to end up right here. So this is negative 2 pi over 4. So this goes to show you that with r, if you ever get a negative value, just go in the opposite direction or 180 degrees away from your specified angle here. Now, just like this one, is there another way of representing this, maybe with a positive r value instead? What angle should I put here if I want to have a positive r? That's right, we're going to have 5 pi over 4. So kind of like how we don't technically need the angles beyond 0 to 2 pi, we could technically get away with only having positive r values. We can make that restriction if we like, but we don't necessarily need to. But yeah, so this shows you how negative r values work. Our final example here, 0 pi. So remember, this is r, this is theta. So what we do is we start here, we rotate around pi angle, pi radians, and then we go out 0 from the origin here. So where am I going to be if I go 0 away from the origin? Yeah, I'm not going to move at all. I'm just going to be at the origin here. So this is 0 pi. All right, now can someone, so it's kind of like these other examples here. Can you guys think of another way of expressing this point? Yeah, like 0, 0, that would also work. Maybe like 0 pi over 4. 0, like a million pi. Yeah, so it doesn't seem to matter what angle we go through if we're not going to move away from the origin. So we're just going to spin around, but we're not going to move away from our origin at all. So a common way that you might see the origin represented actually is just 0 and then theta, because it doesn't matter what your theta values here. It's going to be at the origin for all of them. So this is another way you may see this point written. But moral of the story is if you have r equals 0, it doesn't matter what your theta value is, you're going to be at the origin. All right, so that's plotting some polar coordinates. Now for practice, what I want you guys to do is I want you to take these 4 polar coordinates, or these 4 points that I just gave, and I want you to convert these into Cartesian coordinates. That's going to be a common thing we're going to need to do in Calculus 3. So practice 1, convert the coordinates of the points given in example 1 to Cartesian coordinates. All right, how are we supposed to do that? Well, we have our equations right here. So we have our conversion equations. So if we know what r and theta are, then we could substitute them into these and then get what our x and y coordinates are going to be. So I would recommend using these 2 equations right here. And I'll write the points again just for clarity. So 3 pi over 3, 5 pi over 2. All right. Yes, I'll give you a few minutes to do this. Yeah, this is secretly a unit circle review. What's going on? I can't hear anything over here. Or are you talking about something else? Oh. Oh, no more surprise Pikachu. What does the question say? Convert the coordinates of the points given in example 1 to Cartesian coordinates. All right, give you guys another 30 seconds or so, and then we'll go over this. All right, so let's see here. What are these going to be in our traditional XY coordinates? So let's see here. Let's try to get the X coordinate for this. So X is r cosine theta. So that will be 3 cosine of pi over 3. And if I'm not mistaken, that's going to be 3/2. And then Y will be r sine of theta. So we have 3 sine of pi over 3. So this will be 3√3 over 2. So those are going to be our Cartesian coordinates here. All right, next we have 1 and then 5 pi over 2. So X will be 1 cosine of 5 pi over 2, but that will be 0. And then we have Y is 1 sine of 5 pi over 2, and that will be 1. So this is the point 0, 1 right here. Next, we have -2 pi over 4. And those conversion equations are still valid even if your R is negative. So we have X is -2 cosine of pi over 4. So this is √2 over 2 times 2 is -√2. And Y, as it turns out, will be the same. So we have -√2, -√2. And then finally 0 pi, well, we just spent a bunch of time talking about what that was. That's just going to be the origin right here. Oh, wait a minute. Did the LaTeX not compile on the quiz? Are you seeing a bunch of gobbledygook? Oh, geez. I thought they fixed that. They told me they fixed that. I'm sorry. Hopefully it's readable. Yeah, Canvas is Garbo. I absolutely agree. All right. Well, hopefully you guys can see this, see these answers clearly enough. All right. So in addition to converting individual points back and forth between Cartesian and polar coordinates, we can also convert different expressions or functions in between Cartesian and polar coordinates. So for example, whoops, I skipped example 2, my mistake. So this was converting polar into Cartesian. I guess we didn't do any Cartesian to polar. Convert 1, 1, 3, 0, -3, 4, and 0, 0 to polar coordinates. Okay, so we'll do this and then we'll convert some functions. All right, so we have X is 1 and Y is 1. So for this problem right here, we use the X equals R cosine theta, Y equals R sine theta more. Now for doing it this way, we're more going to use X squared plus Y squared is R squared, and tangent of theta is Y over X. So for our first point, 1, 1, what we're going to do is we're going to put this into here. So we have 1 squared plus 1 squared is R squared, which is 2. So R can be plus or minus the square root of 2. Now, depending on which one of these we take, that's going to affect the angle that we're going to have right here. All right, so I'm just going to select positive R for simplicity. So I'm going to have R as positive √2. And then if I plug these into my tangent equation here, I have tangent of theta is 1. Now we know the point 1, 1 is in the first quadrant, right? So what angle makes tangent be 1 in the first quadrant? It's pi over 4, that's right. Okay, so this coordinate will be √2 and then pi over 4. That will be what 1, 1 will be. All right, let's go to 3, 0, see what this is. Let's see here. So if we use x squared plus y squared is r squared, we have 3 squared plus 0 squared is r squared, implying that r is plus or minus 3. And once again, I'll just pick positive 3, just for simplicity here. And then what we're going to do is we're going to use tangent of theta is 0 over 3 or 0. Okay, so tangent of theta will be 0 when theta itself is 0 right here. So actually, this is kind of funny. These are the xy coordinates, but they're also the r and theta coordinates. I don't think this happens very often. So we have r and theta right here. So they actually are written the same way in both ways. All right, next we have x is -3 and y is 4. All right, so we have -3 squared plus 4 squared is r squared. What am I going to use this time? What is r going to end up being right here? It's going to be 5. That's right. You may remember this from it being a 3, 4, 5 triangle. So we have r is 5, and then we're going to have tangent of theta is going to be -4/3 right here. Okay, that's kind of strange. Now, I don't know a common unit circle angle that's going to make tangent be -4/3. So what we might do here is we could do theta is arctan of -4/3. Now, this won't actually be right. So this is what I was warning you guys about earlier. So which quadrant is the point -3, 4? Which quadrant is that in? It's in quadrant 2, right? -x, +y. So that's going to be right here. Now remember, arctan takes on values between -pi/2 and pi/2, right? So arctan can only give us values in here. So arctan of -4/3, that's actually going to be the point that's opposite to it down here. So what we're going to do here is we're going to have theta as arctan -4/3 plus pi. So the moral of the story is if your point is going to be in quadrant 2 or quadrant 3, then you're going to want to add pi to your arctan. But if you end up getting something in quadrant 1 or 4, then you don't need to add pi to arctan because arctan already can be -pi/2 to pi/2. All right, so we had a little bit of difficulty with this theta right here. All right, and then we have 0, 0. Well, remember how this was expressed. This is going to be 0 theta because we can have any theta we like if our r value is going to be 0 right here. Let me write this a little more clearly. So quadrant 2 or 3, theta is arctan of y/x plus pi. And then quadrant 1 or 4, theta is going to be arctan of y/x. And this assumes positive r, by the way. This is positive r. All right. Why do we omit the negative radii? You don't have to. We could have rewritten a lot of these polar coordinates differently. So for example, for this one, I could have written this as -3 pi. I don't know. I suppose I just have a bias towards using positive numbers. But we could have used negative radii for any of these, and it would have worked. But our theta would have had to be different. All right, now that we've done that, now we can go to converting functions and expressions between polar and Cartesian coordinates. And this is going to be probably the thing we do the most in Calc 3 from this thing here. Is theta 0 for that last coordinate? No, theta, we just write this as theta because remember for the origin, theta can be anything we want. It's really the r being 0 is the significant part right here. All right, so let's do example 3 and then I'll have you guys do a similar example. Convert x squared plus y squared equals 25 and y equals 2x into polar coordinates. Okay, so this is where we're really going to begin seeing the utility of polar coordinates, because some things are going to be easier in polar coordinates, and then we'll also see that some things will be more difficult in polar coordinates as well. All right, so let's remember our conversion equation. So let me put this on the screen here. So here are our 4 conversion equations there. So let's try to use these to change all of the x and y's, get rid of all those, and just only have r's and or thetas. All right, now this one's pretty straightforward, I think, because we actually see something that looks remarkably similar to this on our conversion equations here. What is this going to turn into? Okay, Giovanni, want to step ahead here? Yeah, so we can write this as r squared, because x squared plus y squared equals r squared. And then what we could do is we could take the square root of this, and then we either have r equals 5 or r equals -5. So we could do either one of these. Either one of these is a correct way of labeling this here. Now, what type of figure does this represent? What kind of shape is this? It's a circle of radius 5 centered at the origin, right? So we were to draw that, it would look like this. So that means that if we just have r equals a number, this is going to be a circle of radius that number centered at the origin. So rather than having to square things and add them together and have multiple variables here, we literally have a constant function. And that's how we represent circles centered at the origin. And that is going to be an immensely useful fact when we get to calculus 3 here. So circles in polar coordinates, that deserves a smiley face. Those are going to go pretty well. So we just represent r equals number. It'll be a bit different for circles not centered at the origin, but we'll get to that in a bit. All right, now let's go ahead and try to convert this one over. So y equals 2x. Okay, well, let's see here. So I see y and x right here, right? So I guess I'll substitute these in to get my r's and thetas showing up. So I have r sine of theta is 2 times r cosine of theta right here. Now, assuming my r isn't 0, which the next case will include anyway, I'm just going to cancel these out. So I have sine of theta is 2 cosine of theta, or tangent of theta equals 2. Or another way of saying this is that theta is arctangent of 2. All right, so now we know how to draw this, right? We have y equals 2x. So this is going to be a diagonal line with kind of a steeper slope, looking like this. So a relatively simple form for that. But here we have to use a trig function in order to get our line. Now that's not too bad. I mean, this isn't an awful equation. It's not, it's not the worst thing in the world, but it's probably a bit more complicated than this right here. So, and then this angle theta is arctangent of 2. And one thing interesting about this, notice that the r is missing, right? So since the r is missing, there's no restriction on r whatsoever. So r could be 1, it could be 100, it could be 0, it could be -50, whatever. So r could be anything. So if we're looking in the theta equals arctangent of 2 direction, we can go out any distance we want, or any negative distance. That will also get us this half of the line right here. So that's how lines work in polar coordinates. And lines that go through the origin aren't too bad in polar coordinates, but lines that do not go through the origin are not very good. All right. So let's see. Why don't you guys give this a shot now, except going the other way. So here's our second practice problem here. Convert r equals 8 and r equals 2 secant of theta into rectangular coordinates. Now, when I say convert into rectangular coordinates, I mean get rid of every single r or theta that shows up and replace them all with x's and or y's. That's our goal for this. Yeah. Yeah, so from our conversion, yeah, so we were asked where did this step, or how did this step happen in the audience? We used our conversion equation. So x is our cosine of theta, and we substituted that into here. And then we did r y equals r sine of theta, and we put it into that side. So we just used the conversion equation. Are we going to get to do the awesome graphs like the cardioid and the limacone? Yeah, we'll be seeing those. Yeah, so kind of like how we can have insane curves like I showed you on the parametric equations today, where there are also some pretty cool looking things with polar coordinates as well. I'll give you another minute or two, and then I want to get to drawing these. I think that's probably the trickiest thing we're going to do today. All right, let's take a look at this. So our first equation, r equals 8. Now, we've already seen something similar to that in the previous problem. We saw what happened when we had r equals 5, right? So this is a circle of radius 5 centered at the origin. So as you can imagine, this is going to be a circle of radius 8 centered at the origin. And how do we write that in Cartesian coordinates? Well, we can square both sides and have r squared is 64. And then from our conversion equations, we know that r squared is x squared plus y squared. So this is what we're going to have for our Cartesian coordinates right here. No, it's not the Pikachu graph, unfortunately. All right, and then we have r equals 2 secant of theta. Now this one's a little bit trickier. Now we have something in the conversion equations about r times cosine of theta, but we don't have anything about secant, but we can remedy that by multiplying both sides by cosine of theta. So we have r cosine of theta is 2 secant of theta cosine of theta, and these are reciprocals of one another. So we just get 2. All right, and then r cosine of theta, what's another way of saying r cosine of theta? It's just going to be x. That's right. So x equals 2. So this is what we're going to get. And what kind of graph is this? It's going to be a vertical line at x equals 2. So I would much rather write just x equals a constant rather than r equals 2 times an uncommon trig function, 2 secant of theta. So in this case, polar coordinates are frowny face. They're not quite as good as Cartesian coordinates. If we had to choose between them, we would probably choose the Cartesian coordinates right here. All right. But fortunately, it's rather uncommon for you to be forced to write lines in terms of polar coordinates. Most of the time, we can get away with using Cartesians in those cases. All right, so there we go. So that's enough about conversion. Now I wanted to show you guys how to graph with polar coordinates here. All right. Yeah, what's up? So, so the question was, where does y show up in here? Why don't we have that? Well, kind of like how back here, we have theta is arctan of 2, and then r can be any value. All we need is x to be 2 here, and then y can be any value. So as long as x equals 2, y can be 1, it could be 0, it could be -1, it could be 100 million, whatever. So y could be any value whatsoever. Yeah. Yes, so this equation right here, r cosine of theta, this is how we get x right here. That's how we get x from polar coordinates. All right. So let's try to draw a curve here. Example 4. Let's sketch the curve r equals cosine of theta. All right, so this should be a relatively simple curve to draw here. Now, your math teacher in high school may have advised against this, but what we're going to be doing is we're going to graph this by plotting points. So that's what we're going to do here. So what I'm going to do is I'm going to have a bunch of theta values, and I'll write the corresponding r value here. And this is a surprisingly effective method for plotting these polar graphs. All right, I think I'm going to go by intervals of pi over 4. I think that'll be enough to capture what's going on here. I'm going to start at theta equals 0. And if I plug 0 in for my cosine, I get 1 right here. So I go in the theta equals 0 direction, I go out 1 unit, which I guess I'll say is right here. All right. Next, we'll have pi over 4. Cosine of pi over 4 is root 2 over 2, or about 0.7-ish, so a little bit closer. So we go in the pi over 4 direction, and we go a little bit closer to the origin. And what we want to do is we kind of want to connect these by a sort of a curved arc right here. That's usually how we do it with polar coordinates. Next, we have pi over 2. Cosine of pi over 2 is going to be 0. Okay, so this is where things start to get interesting. Remember, r being 0, doesn't matter what the angle is, we're going to be at the origin. So as we get close to the angle pi over 2, so as we're rotating this way, as we're starting to get close to pi over 2, our point is coming closer and closer to the origin until finally we get to pi over 2, and we're at the origin. So we end up having this right here. Okay, now the next bit's a little bit weird. So let's go to 3 pi over 4. That'd be our next coordinate that we would draw. What is cosine of 3 pi over 4? What's that? Yeah, that's right. So it's going to be negative root 2 over 2. So this means that once we get past pi over 2, cosine will begin being negative. Now, we talked earlier about what happens with negative r values. So what's happening is we're starting to rotate to these angles right here. R is actually going in the opposite direction of those angles because it's negative. And so when we get to 3 pi over 4, which is maybe like this, rather than going root 2 over 2 this way, we're going root 2 over 2 in the opposite direction, which will land us right here. And then let's get to pi right here. Cosine of pi is the most negative the cosine can be. It's negative 1. So as we rotate further toward our angle pi here, we're going to get more and more negative. So we're extending outwards in the opposite direction even more. And then we actually end up back where we started. So we're in the pi direction, but we go negative 1. All right, that's interesting. So we end up back where we started, but maybe we'll start going a different direction now or something like that. So let's do 5 pi over 4. Cosine of 5 pi over 4 is also negative. It's negative root 2 over 2. Now 5 pi over 4 is in this direction, right? But we're going to go the opposite direction, root 2 over 2. But that's actually just going to take us to this point. So it actually seems like we're traveling over the same path once again. So I think it's pretty safe to kind of stop things right here. It seems like we were able to get all of our curve. And if we keep going, we're just going to keep revolving around this shape right here. Are we going to deal with I? That's a very good question. We might. I'll let you know when that happens. Yeah, there's kind of an interesting scenario with that we'll see in the future. All right, now what shape is this? What shape does this seem to be? You don't have to think too hard. It's just a circle. So this is a circle of radius 1/2. Now, unlike the circles that are constant r values, this is not centered at the origin. This is centered at the point 1/2, 0. So in general, if I have r equals some constant a times cosine of theta, this will be a circle of radius or diameter, excuse me, a, and then I'll put this in quotes, in the x direction. So the left side of the circle will just touch the origin and then extends outwards in the x direction. Now, based on this right here, based on this fact, how would you describe this polar curve? R equals a sine of theta. Oh, I guess I'm assuming a is greater than 0. So what r equals a sine of theta? What do you think that would be? Yeah. Yeah, that's right. So this one's going to be extending, it's going to be tangent to the x-axis, and it's going to extend in the y direction. It's going to have a diameter a in the y direction. That's right. These are so this would be like, say, r equals sine of theta right here. Okay, well, that's all well and good here, but we already knew how to draw circles, even ones that weren't centered at the origin. So let's see something unique that polar coordinates can offer us, or at least something that's much harder to describe in Cartesian coordinates. For our final example of the day, hopefully I'll be able to get through this. I think I will. I want to plot one more curve. I want to plot r equals 2 sine of 2 theta. So this one's a little bit different because we have a coefficient on the inside of our argument here. Okay, so let's go by pi over 4s again. I think that worked pretty well last time. Let's give it another shot. All right, so we have 0. Sine of 0 is 0. So we start at the origin right here. We go to pi over 4. Sine of 2 times pi over 4 is sine of pi over 2, which is 1. And then times 2 is 2. So when we're looking at pi over 4, we extend from not being away from the origin at all to being about, let's say this is 2. So we're going to extend like that. And then with pi over 2, we have 2 times sine of pi. Now, sine of pi is 0. So interestingly enough, once we come out here to 2, we're immediately going to retreat back to the origin. And then by the time we get to the angle pi over 2, which is in the positive y direction here, we're going to be back here. So we've kind of made this sort of oblong looking petal shape right here. Okay, 3 pi over 4 times 2, that'll be 3 pi over 2. Sine of that is -1. And then times 2, it'll be -2. So now, as we're moving in the 3 pi over 4 direction, that means we're rotating out this way right here. We're going to begin going the opposite way. So remember how the negative r values work. So we're going to go in the opposite way to 3 pi over 4. How do I know to curve them like that? If I'm being rigorous about this, I really should verify whether it's curved this way or maybe it's kind of flatter. I kind of just puff it out. I kind of just puff it outwards. I know that's that's not very specific, but I try to make everything kind of look like little circles here. That usually gets you the right shape when you're drawing polar coordinates. All right, so anyways, we're going out to here now, and this is at 3 pi over 4. And then when we get to pi, we have sine of 2 pi is 0. So it seems like we're alternating between 0, a number, 0, the negative, 0. So when we get to pi, which is this angle, we're going to come in like that. So we get another one of these petals here. Okay, now you might be like, okay, well, we got to pi here and we saw what happened last time we got to pi. We're just going to quit, but not necessarily. Let's keep going here to make sure we don't have anything more happening. Let's see, 5 pi over 4. If I plug this into here, I have sine of 5 pi over 2, which is 1. And I multiply that by 2. All right, so I think we can pretty clearly see the pattern here in the r values if I go by pi's over 4. So 5 pi over 4 is this way, but now I'm back to the r being positive. So I will actually go in that direction. So I'm going to go out this way. And then we end up having 3 pi over 2 for our next one. That will be 0. So that will come back in here and we'll hit the origin by the time we're in the 3 pi over 2 direction. And then I bet you could predict what's going to happen. We're probably going to have something right here. We have 7 pi over 4 next, -2. So 7 pi over 4 is normally in this direction, but instead we go the other way. And then finally we get to 2 pi. Sine of 4 pi, when we plug that in, it'll be 0. And then we come back here. Okay, now just to be certain, it might be like, oh, well, maybe we'll start kind of shooting up petals like in between these or something like that. So if we want, we can go to like 9 pi over 4. That'll be 9 pi over 2. But that will actually just lead us along this first petal that we drew again. So once we start retracing the same path, then we know we've finished this here. So we end up with this very pretty looking flower right here. So this is a flower of 4 petals right here. So that's kind of a unique thing. And there may be a way of expressing this in terms of Cartesian coordinates. Yeah, I think there would be actually, but it would be really complicated as compared to this. So yeah, this kind of shows you where polar coordinates really get to kind of come in here. What's the hybridization? Oh man, we're not in biology. I think I'm going to ignore that. But there actually is kind of a formula for these. So if we have r equals sine or perhaps cosine of an even number times theta, it'll be a flower. So let's say this is n. N is even. Then this will be a flower of 2n petals. So for example, if this were sine of 4 theta, we would end up having 8 petals if we went all the way through here. And then if we have r equals sine or cosine of an odd number, which I guess I'll call n as well, times theta, it will be a flower of n petals. So technically, technically we can kind of imagine back here that this circle is a flower of 1 petal in kind of a weird way. But if we have an odd number here, like for example, if we have sine of 3 theta, we would actually only produce 3 petals here. So that's kind of the formula for that, how these go. All right, so that's about it for today. Next time, we're going to talk more about polar coordinates, and we're going to begin talking about the calculus of polar coordinates. So we're going to begin trying to find areas, like for example, we would try to find the area enclosed within these petals right here. We're going to see a way to do that right here. All right, so that's it for today. So I will see you all on Friday.